Here's our Unit 1 review for AP Physics 2 Fluid Mechanics. First key idea, the behavior of molecules gives rise to pressure and the forces that pressure can produce. Static fluids are fluids that are sitting still. Pressure at any point in a fluid is caused by the weight of the column of fluid above that point plus the pressure acting on the surface of that column of fluid. This formula so if we have a pressure out here, usually it's atmospheric pressure, which is 1.01 times 10 to the 5th pascals, and we've got a height to the surface of the fluid. We would say that the total pressure is the atmospheric pressure plus rho, that's the density of the fluid, times G times H. Therefore, the greater the height of that column, the greater the pressure at the bottom of the column. Again, the pressure is dependent on this height. Absolute pressure is the difference between the measured pressure and a vacuum. Gauge pressure is the difference between the measured pressure and the atmospheric pressure. So this is absolute pressure. This is usually atmospheric pressure, although there are situations where we have a closed, say we have a can, and inside the can there's liquid, and then there's gas here. You could have a pressure different if this were a closed can, pressure different than the atmospheric pressure is possible. And this portion is the gauge pressure. Again, that's the pressure due to depth. Part C, Eureka! Archimedes' principle states that the buoyant force on a submerged object is based on the weight of the displaced fluid. Weight of the displaced fluid. This is weird. We're just going to cross this out. And this pressure creates an increase on all points inside the fluid. So a couple things. First of all, let's suppose, again, I've got a container of water. Now let's say I drop a rock into the container of water. What happens? The liquid rises so that the volume of the displaced liquid equals the volume of that rock. The rising water creates a corresponding change in pressure because the height changed. Okay, and then Archimedes' principle again says that this buoyant force is going to be equal to the density of the fluid times the volume of the object under the water times G. If the object is floating, then only a portion of it is underwater. Pascal's principle states that any increase in pressure on the surface of the fluid creates an equal and undiminished increase, increase in pressure in all points throughout the fluid. Okay, so that's the same thing that we set up here. Again, got a vessel of water, I throw a rock in it, the water level rises and therefore increases the pressure everywhere. Dynamic fluids, fluids in motion. Conservation of mass leads us to the continuity equation. This is the continuity equation. A1V1 equals A2V2. This is for a pipe with a changing cross-sectional area. And we know that the speed will be greater where the area is smaller. The continuity equation can be altered to give mass flow rate and volumetric flow rate. So if you just look at half of this, it'll give us the volume per time. Because what do we have here? We've got meters squared times meters per second or meters cubed per second. So just half of this, again, is called the flow rate. Conservation of energy leads us to Bernoulli's equation, which is used to relate the velocity, pressure, and height of a flowing fluid from one point to a fluid flow in another. So Bernoulli's equation is really helpful when the height is changing, the cross-sectional area is changing, and the velocity is changing. So here's an equation review. Pressure is force over area. Density is mass over volume. Here's our pressure in a static column of fluid. Buoyancy, continuity, and Bernoulli's equation. Got a little bonus here, volumetric flow rate. So I showed you AV being cross-sectional area times velocity. Oops. But this is also equivalent to volume per unit time. These two things are equivalent concepts. Okay, final big ideas. Pressure is caused by the random thermal motion of the molecules. So molecules have to have some temperature above zero in order to have some pressure. Gravitational force increases pressure. The deeper inside of a fluid you go, the higher the pressure gets. The force caused by pressure is always perpendicular to the surface of contact. So if I'm inside of a glass jar, the pressure is going to be perpendicular or normal to the walls. Pressure equals force divided by area. The density is mass divided by volume. Absolute pressure, again, we've talked about that. Absolute pressure is equal to atmospheric pressure plus rho g h. The buoyant force is equal to the weight of the fluid displaced by that object. This, by the way, is called Archimedes' principle. Oopsie. If a force is applied somewhere on a container holding a fluid, the pressure increases. So maybe a better way to say that, let's say that I've got some water in a container, and now let's say that I put a ball floating in the container, and what's going to happen is the water level is going to rise, and that's going to raise the pressure everywhere in that container. Let's see, the volume flow rate is the same everywhere in the fluid. So the volume flow rate, again, is equal to the cross-sectional area of a pipe times the volume in that pipe. And finally, Bernoulli's equation is a statement of conservation of energy, and it tells us when velocity of a fluid stream increases, the pressure in that stream decreases.